Hi, welcome. This is Yichun Wang and this is my first video. Since I'm applying for an opening position of robotics software engineer, perception and localization, the first three videos will be about perception and the last two will be more about localization and SLAM. This is a project I'm currently working on. This project is held by University of Florida and Florida Department of Transportation. My duty is use LiDAR point cloud data, classify the pedestrians near traffic intersections. Getting a bag of point cloud data, I divided the project into 4 steps. The first is ground removal and it's already done by June 21st. The second one is non-ground removal, non-ground segmentation. It's also done. And I'm currently on the pedestrian detection, which is training a machine learning classifier to detect whether the clustered point cloud is a pedestrian or not. Then after this, I will apply adding tracking algorithm for each pedestrians. The intuition of ground removal is a point cloud library function, which is plane model segmentation. But it's too slow with tens of thousands of points since it's utilizing ransack algorithm. I applied the lowest point representative on it to solve the problem. I don't think it's necessary to go over the math for now, but you are more than welcome to pause to read how I solve this problem. And the runtime of ground removal is shown here. Then I would cluster the non-ground point clouds. Again, the intuition here is utilizing existing point cloud function, which is Euclidean distance cluster extraction. And this is my results from utilizing KT dataset. The clustered result. You can see different cluster have different color label, and the KT dataset is created with 64 beam LiDAR data, but ours only have 16 beams. This is the KT dataset. And our 16 beam LiDAR immediately created a problem, which is as long as the pedestrians are a little far away from sensor, you can see the point clouds immediately became too sparse to be recognized as a cluster. I solved this problem by mapping all point clouds into ground. Cluster the squashed clusters. Return the indices of points in each cluster and get it back to the original 3D data. The algorithm improved dramatically after my modification. Now let's see some results. And this is a segment. So the raw data will be like this. The different color means different intensity from laser beams. And the ground is marked as gray and the non-ground segments are marked as blue. And the algorithm starts to cluster and segment pedestrians. And this is traffic lights in the opposite across the street. You can see the cluster algorithms still working. Again, let me show you more about this ground and this non-ground. and this is a cluster. After the classification, no, after the clustering, then we need to build a machine learning classifier to do pedestrian detection. I was planning to train support vector machine, but its disadvantages are over the advantage. So we decide today after a meeting to build the support vector machine, but train a neural network classifier to do pedestrian point cloud detection. This will be my work in the next few weeks. And let me show you why we built the support vector machine. The support vector machine is very fragile to the environment. As long as there is something changed in the environment, it cannot do a well work. Like in this demo, I mean, it's working. It's doing classification on a human being, but there are just way too many false positives. So we built this. This is not robust enough. So we are moving on to neural network one. Okay, thank you for watching my first video. See you in the next one.